Can we discuss
It's very
later?
quick.
Yeah.
So it's question 3. We're drawing 2 balls. Does order matter?
Yeah, matters.
Okay.
Okay. Good afternoon, everyone. Let's start. Yeah, sorry for being a little bit late today because of this setting issues. Okay. So again, just reminder, don't forget to finish your homework one on time, and also we got some quiz due tomorrow. Okay. Okay, let us continue with the probability. Okay. In the last lecture, we talked about the rule is called the total probability. Right? So basically, it associates with how are you gonna compute the probability with one event with another set of events, right? So here's just a quick review, right? So if we want to compute the probability for a particular event A, right? So in many scenarios, you will find that it's not very easy to compute that. So a convenient way or a convenient strategy will often be, okay, I'm gonna introduce a set of other events, B1, B2 through Bn. We require that those n events can partition the whole sample space. Right? By partition, it means that each of those events takes one portion of the sample space. Those events are not overlapping with each other. That's it means what it means for partition. And then we can compute the probability of the event A as, sorry, I don't know why it's disappear again. One second. Okay, here we go. Oops. This line is really unstable. So it is equal to, we first compute the probability of B1, then times the conditional probability of even A given B1, and then plus the probability of B2 times the conditional probability of A given B2. And you just add up, right? So until you add the probability of Bn times the conditional probability of A given Bn. So a visualization example which we have discussed is given like this, right? So this big circle is a whole sample space. We want to compute the inner circle. A, right? The probability of even A, right? So how do we compute that? We can partition this big circle omega into 4 parts, B1, B2, B3, B4. They represent 4 events. They are not overlapping with each other, but they jointly cover the whole sample space. Then we can write the probability of P of A as the probability of B1 times the conditional probability of A given B1 plus probability of B2 times the conditional probability of A given B2 plus probability of B3 times the conditional probability of A given B3. And finally, probability of B4 times the conditional probability of A given B4. Right? That's the total probability. Right? You can view it as a divide and conquer strategy, right? I want to compute some kind of event which has which corresponding to the one diagram has a like complex shape. It's hard to compute them once and for all. How can we do that? Let us introduce another set of events which can nicely partition the whole sample space. Then we decompose the computation into the probability of each event and multiply the conditional probability of the target event condition on this event. That's the idea. Okay. And then one very useful and simplified version for this is just to consider one another event, right? So for any event B, we consider B and B complement, right? Remember B and B complement, their union will be the whole sample space. And B and B complement, they won't overlap, right? Then we can decompose the probability of any even A as probability of B times the conditional probability of A given B, right? Plus the probability of B complement times the conditional probability of A given B complement. Right? Okay, any questions so far? We're just quickly reviewing what we have discussed throughout last lecture. Okay, and then we did a few practice, right? The problems, and of course we have seen these problems for a few times, right? Pick 2 urns and pick balls and pick the urn and then pick the ball, right? We're not gonna repeat our calculation. We just want to mention that we'll use this total probability to compute the probability for some kind of event. It is actually a rigorous formal representation of the tree diagram we have used, right? So previously, when we want to compute the probability, say for event A, I would just draw a tree diagram and we'll consider several events, right? Say here, it will be, okay, first we pick up an urn, right? If we pick urn 1 with half probability, right? And then given urn 1, you got 3/7 chance to pick white ball and 4/7 chance to pick black ball, right? And also you enumerate another pass, which at the beginning, you picked urn 2 with probability half, and then given N2, you have some probability to select Y ball, some probability to select Y ball, and overall you want to look at what is the marginal probability of selecting Y ball. What shall we do? We just pick out all the passes which reaches Y ball, right? And add them together. Right? This literally is just an execution of the total probability. Hopefully, everyone can make a correspondence between these two, right? It actually comes from or justified from this total probability. Okay. Another practice is about power supply failure. So I highly recommend every one of you to replicate the derivation and calculation as we did in the lecture, because all your homework problems and also the final exam won't escape from this, right? So if you feel super comfortable about those examples, you will feel super comfortable about homework assignments and about your problems appearing in your final exam. Okay, any questions so far? Okay, great. So today we're going to talk about Bayes rule. Right? So this is a very, very important concept, and also it's kind of like a cornerstone of machine learning, or more specifically, probabilistic machine learning, because I'm a guy who is doing like machine learning, especially probabilistic machine learning. So I've used Bayes rule to do my modeling, to do my justification of my work every day. So I'm super familiar with that, and I'm fully aware of its importance. But interestingly, you see that Bayes rule can be derived with very simple principles and the rule we have discussed so far. So let's see, right? So let us first review the definition of the conditional probability, right? So so far we have defined what does it mean for conditional probability. We talk about two events, right? One event is A and the other event is B, right? Conditional probability means, okay, given the occurrence of event B, what's the probability of event A to happen, right? That's the natural language explanation. Then mathematically, we calculate conditional probability in this way. We're going to divide the joint probability of A and B. By joint probability, it means the probability of A intersection with B. Right? We're going to divide this joint probability by the marginal probability of event B. Right? So one way to memorize this is consider the numerator is always the joint probability, naming the probability of the intersection of two events, right? And the denominator actually is the probability for the conditioned part. Right here, it is conditioned on B, so the denominator will be the probability of B. Right? That's our definition of conditional probability. Right? So what is Bayes rule? Right? Bayes rule allows us to switch the order of A and B. So basically, it tells us how can we, according to this, or how can we make the relationship between P of A given B and P of B given A. It reveals the relationship between these two conditional probabilities. Right? Remember, it's just a switched order. Right? The first one is A condition B. The second one is B condition A. And Bayes rule tells us, okay, what's their relationship? Right? And conceptually, they're different, right? Conceptually different, and numerical, they most likely they won't be. They are different as well. I consider actual case like say given say A could be A could be like the stock price arises, right? Big would be there's a big snow, right? So conditional there's a big snow, the stock price arises. This is different from like conditional on stock prices and then there's a big snow, right? This is two things. They represent two different concepts. And then mathematically, how do we build up the relationship? So we're gonna going back to the definition of the conditional probability. So from here, from the original definition of conditional probability, right? This guy, right? PA condition B equals to PA intersection B over P of B, right? We just multiply P of B to the left-hand side, right? Move to the left-hand side. Then we get this, right? So we have the P intersection of P of A intersection with B equals to P of B times P of the conditional probability of A condition on B, right? So we know that the probability of A intersection with B is the same as probability of B intersection with A, right? Why is this correct? Why is probability of A intersection with B is the same as probability of B intersection with A? Yes, exactly, right? Remember, we actually this is the this is the law for the sets, right? So if you switch the order of the sets during the intersection, it doesn't change, right? And similar rule applies to union, right? So and then when we look at this, right? P of B intersection with A, you apply this result again. Here you can just view it. I'm gonna replace here, like here, I'm gonna replace A by B and replace B by A. It's the same thing, right? You just change the symbol, right? The result will be same, but then the right-hand side will be the marginal probability of A times the conditional probability of B condition on A, right? Oops. And now we see that the left-hand side actually, I mean, of the two equations actually the same, right? Then that means the right-hand side should be the same as well, right? I mean, left-hand side just telling that how left-hand side just about the joint probability of A and B, right? And the right-hand side is just expressed in two expressions, right? That means definitely these two expressions should be the same, right? So that gives us this equation, right? That is the probability of B times the conditional probability of A given B should be the same as probability of A times the conditional probability of B given A, right? And then if you look at this, right, conditional probability of B given A, if we divide both sides by P of A, right? So this guy will be canceled. Those guys will be canceled on the right hand side, right? So it gives us a formula where the conditional probability of B given A is the conditional probability of the marginal probability of B times the conditional probability of A given B, then divided by the probability of A, right? Yeah, that's called Bayes rule. So what does it mean, right? What kind of result, interesting results does it reflect? Left-hand side is conditional probability of B given A, right? So if you see right-hand side, you see it contains another conditional probability with A and B switched in order, right? So the right-hand side is a conditional probability of A given B, right? The left-hand side is conditional probability of B given A. So now this rule tells us, okay, if we want to look at the quantitative relationship between these two conditional probabilities, here it is. If you want to compute, if you know the conditional probability of A given B, right? Now, if you want to invert it, right? You want to invert it to conditional probability of B given A, then you need to multiply this guy by P of B and divide it by P of A. That is called Bayes rule. Sometimes it's also called Bayes inverting theorem. By inverting, it just means you switch the order in a conditional probability. Any questions so far? Everyone's comfortable? Okay, great. Yeah. So now let us get familiarized with this Bayes rule by doing some kind of practice. Right? So we're gonna use the same setting as we before, so everyone will feel comfortable. Right? Again, we have two urns. Urn one has 4 black balls, 3 white balls. Urn two has 2 black balls and 2 white balls. And you pick up one urn at random, then select the ball from the urn. And we consider two things, right? Two questions. First, what is the probability the ball is white? Right? So we can define the ball is white as the even A, right? And then things are more interesting is that consider another event, which is called you picked the first urn, which we call even B, right? So we're interested to know if you picked a black ball, what's the probability that you had picked the first urn? So this is a conditional probability, right? Does it make sense? Right? So this is a natural language about conditional probability, right? So given that you have picked a black ball, what's the probability that you had picked the first urn? So we should write this as P of B given A complement, right? Any question? Remember here we just defined the event A as the ball is white, right? So here we're talking about the probability condition on you pick a black ball, right? The black ball should be represented as A complement. Does it make sense? Okay. So now let us look at how are we gonna compute this, right? So of course you can use total probability. You can use the tree diagram to calculate all those stuff, right? We have already done this before, right? But now let us try to use Bayes rule. So first, from the setting, we know the inversion of this conditional probability, right? Which is, what is the conditional probability that you pick a black ball, given you pick the first arm? What's that? From the problem setting, can anyone tell me what's the conditional probability you pick a black ball, which is A complement, condition on that you pick the first arm, which is even B? What's that probability? Just 4, 7, yeah. So, okay. Condition on that you pick the first arm, right? Then you pick a black ball. You see that in arm 1, you have 4 black balls, 3 white balls, right? You got the same chance to pick up any ball. So your chance to pick up your chance to pick up a black ball will be 4/7, right? So then what we want to calculate is the invert of this conditional probability. That is, given you pick a black ball, what's the chance you had previously picked the first arm? Right? So we're going to leverage the base rule we just introduced, right? So the formula here, I'm going to erase those drawings to make it clear, right? We just apply this rule. And here, I'm going to just write down. So the conditional probability given A complement should be the conditional probability of A complement times B times the marginal probability B, and then divided by the marginal probability of A complement, right? So this is just a application, straightforward application for this, right? So here we just we use the different symbols, right? So B should be A complement and A should be B, right? If you just replace those guys by the new symbols, it is like this. So if you want to compute the target conditional probability, which is the inversion of this probability, right? We just need to multiply this probability P of A complement given B with the probability of B divided by the probability of A complement. Right. Any questions so far? Everyone feels comfortable? Okay. And then for this guy, right? We've already known, right? It is 4/7, right? We just read through the problem. We know that, right? So how about the probability of B? 1/2, right? It's also, we can see that from the problem, right? We pick one arm at random, right? That means we got equal chance to pick arm 1 and pick arm 2, right? So the probability you pick the first arm, which is B, right? Which represents the even B, right? It's 1/2, right? Then we can see that the remaining question is how to compute the probability of A complement, right? Could anyone suggest the way to compute this? Well, it might not be that straightforward. It kind of leverage the things we have discussed. Go ahead. Mm-hmm. Mm-hmm. Yes, exactly, right? So just connecting what we have discussed before, right? Because everything is connected. So we can just leverage the total probability rule we have discussed, right? So, and to compute P A complement, we can leverage another event, which is just B, right? And then we can use P of B times P of A complement given B plus P of B complement times P of A complement given B complement. Does it make sense? Right, this is just the the simplified version of the total probability. Right? Okay, so let us just calculate, right? So first, P of B, as we mentioned, is 1/2, right? And then what is the conditional probability of A complement given B? 4/7, right? Just read through the statement, right? And then probability of B complement will also be 1/2, right? That means you select the second error, which has the same chance of selecting the first error. Then what is the probability of A complement given B complement? 1/2, right? So you should look at the second statement, right? Given error 2, you got 2 black balls, you got 2 white balls, and the chance you get black ball will be 2 over 4 or 1/2, right? Then you just add them together. You add them together, you get the marginal probability of A complement, right? Maybe I just write it down, right? So this is just 2 over 7 plus 1 over 4, which is 28. 8 plus 4. 8 plus 7 will be 15 over 28, right? So now you got this denominator, which is 15 over 28, right? You just you have all the numbers you needed. You get your conditional probability of B given A complement. Right? Any question? Okay, great. So yep, a little bit more practice, like so that everyone will feel very easy to deal with homework too, right? Okay, again, we can go back to this familiar setting, right? We have a power system and which contains a main power supply and an auxiliary power supply. The main power supply with 10% chance of failure, and auxiliary power supply, it has a 10% chance of failure if the main supply is running. It gets a 15% chance of failure if the main supply fails, right? Okay, so previously we have computed, we have shown that how to compute the probability that the auxiliary power will fail, right? We can use total probability, right? We have discussed about that in the last lecture, right? So again, we're gonna define this event, the auxiliary power fail, as the event A, right? So things are really interesting that when we observe that the auxiliary power fails, can we quantify the probability or the chance that the main power also failed, right? We can define the event main power also failed as event B, right? This actually is about computing the conditional probability of B given A, right? This is conditional probability. Okay? So again, let's try to apply the base rule, right? So first, we look at the invert version of this, right? The inversion of this is P of A given B, right? So what is P of A given B? Anything? P of A given B means that, okay, condition on that the main power field, what's the probability your auxiliary power also fail? What's that probability? Yeah, it's 0.15, right? So here we read them through the problem setting, right? The problem setting actually tells us this conditional probability. Given the main supply fails, the auxiliary power will have a 15% chance of fail, right? That exactly means this probability, the conditional probability of A given B. Does this make sense? Right? So let us just write down, which is 0.15, right? Again, we want to apply the chain rule, not chain rule, the base rule to compute P of B given A, right? So I'm just copy down the base rule here. You're going to multiply it inversion P of A given B times the probability of B and divided by the probability of A, right? This guy, we know is 0.15, right? We all agree with that, right? So what's the probability of B? What's P of B? Can speak a little loudly. 0.1, right? We can see that from the first statement, right? The main supply has 10% chance of failing, right? So this guy is 0.1, right? Then the remaining is P of A. What is P of A? What is P of A? Oh, I guess you cannot directly read it, right? There's no like explicit clue telling you what is P of A. You have to compute that. Right? And I mean, the good thing is that we have two numbers which can read through, can be directly read from the problem statement. But if you want to compute P of A, you have to do some kind of extra calculation, right? And how do we calculate P of A? Right? Exactly, right? Again, apply the total probability, right? So P of A means the overall probability that the auxiliary power will fail, right? So this contains like several cases, right? Maybe the main power is still running, but then the auxiliary power fails, right? Or maybe the main power has already failed, and then auxiliary power has also failed, right? So that's why we have to use total probability. So the total probability is written as P of B times P of A given B plus P of B complement times P of A given B complement, right? So this guy we know, actually I'm already knowing, right? P of B, probability of failure for main power, 0.1, right? And this guy we have already known, given the main supply fails, the auxiliary supply fails with 0.15 chance, right? So this is 0.15, right? Then how about this guy? What is the probability of B complement? 0.9, right? Because you know P of B is 0.1, of course, the probability of B complement will be 0.9, right? And how about this guy? What's the probability of A given B complement? Y is still 0.1. Yes, yes. So we actually read it from this statement, right? So B complement, B means the main power failed, right? And B complement means the main power is still working, is running, right? And then given the main power still running, the chance this auxiliary supply fails with 10%, right? So that's still got 0.1. Now you just add them together, you get the probability of A, right? Which is 0.015 plus 0.09, which is 0.105. You got your denominator to be 0.105, right? Okay. So hopefully this two practices will give you a sense like how can we leverage this so-called Bayes rule to invert conditional probabilities? Because this is I mean, really useful in practice. Because in many cases, like P of A given B is like causal effect, meaning that some kind of event A is caused by B, right? Say you see your car stuck, right? Your cars is broken at the road or cannot run on the road, right? And okay, if you run out of gas, okay, you got a chance to have your car stuck at the road, right? Or maybe your battery is dead, you make your car stuck, or any other mechanical malfunction, right? And this is called a forward model. You have some like a forward causal event happens, it leads to some consequence. Right? You have like very well designed, very well understanding about those effects, right? But in practice, things are always like in the reverse case. Like for example, I don't know what happens inside my car, but my car just stuck and it doesn't drive. I cannot drive. It just I have to pull over on the road and wait for road assistance, right? And then I would like to know, okay, given my car stuck, right? Given my car is there cannot run anymore, what's the possibility my battery is dead? Or what's the possibility my gear has some problematic? What's the probability maybe some belt in the engine eroded and fell off, right? There are kind of all kinds of probabilities. So we need this tool to help us to quantify the possibilities of different reasons and how likely of each possible causes. This will be very, very important for complex system like you have a space shuttle, you got SpaceX, you got a big rockets, right? And what you can observe is that your rockets just blasted and into pieces, right? Like going through the sky, right? And then the question is that given your observations, given your measurement data, how can you infer what's the likely causes of those accidents, right? Okay, yeah, let's just rest for 5 minutes and let us continue. Okay. Yeah, let's continue. So here, I just want to briefly introduce how Bayes' rule is formulated in the machine learning domain, because this is my territory. So how Bayes' rule is used in machine learning or artificial intelligence, I mean, broader sense, right? So usually people will consider Bayes' rules application in this way. So we usually build up some kind of model. This model could be a support vector machine, could be a Gaussian process, or very big neural networks. It could be transformers, it could be convolutional neural nets, it could be recurrent neural nets, and so on. You name it, right? There are many, many possible models, right? And also, to conduct machine learning or artificial intelligence, we have to collect a lot of data, right? It could be supervised data, labeled data, unlabeled data, whatever data, right? So what does machine learning do, right? So machine learning essentially is trying to find out this guy or approximate this guy. Namely, given the current data in my hand, it probably is not in my hand, it's in a big storage or cloud storage, super big, right? What's the chance or what's the likelihood that my particular model will be the ground truth model or will be the best model to describe the word, right? So by here, like my model means that, okay, I could choose a very big transformer model. It could be recurrent neural network model. It could be a simple probabilistic model, or random forest features, whatever machine learning model, right? We want to know, given the training data in my hand, right, which model I should use, and which model under which set of parameters should we use. And to do this, right, to compute this, you see that it usually computationally infeasible, because this Bayes rule is very, very hard to compute, right? But that's why people have come out a lot of like approximations. But the framework remains unchanged. It's always like, I'm gonna look at the numerator first, right? The numerator will be, okay, what's my probability of the model? The ground truth model should be like this. It contains some of our prior beliefs or our empirical evidence showing that, okay, it is highly likely that it is this random forest should be the best fit to this data or the word or the problem, or could be the neural network should be the one we should choose, right? And then we should look at, given the model itself, how the model will generate the data. Like suppose you're given a set of images, right? We want to describe or want to calculate, given my current 256 layer neural networks, convolutional neural nets, how likely the data is generated by my model. This is actually the core design or core problem of the machine learning applications, right? And if you can do this very smartly, and then you got a chance that your model will have very high likelihood to generate data. That means your model, in this sense, right, conditional data will be more likely to be the ground truth, or more closely to the ground truth, which really describe those data. Yeah, that's the basic frame, right? And of course, there will be a lot of like challenges in terms of not only the design, but also once you design this, how do you effectively calculate this, right? Because this marginal probability of data D is very, very hard to compute. It usually doesn't have any closed form, and you have to approximate in a variety of ways. That form the big branch of machine learning and artificial intelligence research area. Okay. Okay, so in the remaining discussion of our lecture, would like to do some kind of brain teaser. This is a very classical problem, but I believe that this kind of problem can strengthen our understanding about the probability, conditional probability, those kind of stuff. So this problem is called Monty Hall problem. How many of you have heard of this? Oh, nice. Did you guys read the book? Oh, nice. Okay. Okay. Then it will be easier to go through this problem. Okay. So I'm still gonna quickly introduce this game. Right? So you're on game show. Right? There are 3 doors. Okay. And there's one door behind is a car. And for the remaining 2 doors behind are goats. Right? You're invited to random pick up a door. Of course, if you are lucky enough, you win a car, right? Otherwise, you can only bring the goat. So suppose you pick a door, number 1 door, and then the host, who knows where the car really is, right? He opens another door. We say door number 3. And when he opens the door, you see a goat coming out from the gate. Now, you have 2 choices. You stick your first choice. You choose gate 1 to open and check if you are lucky enough to get a car. Or you switch your choice to look at gate 2, and to see whether you have a better chance to have the car. Now the question is, which choice would you like to make? Do you want to stay with your first choice, gate 1, or you want to switch to gate 2? Or you believe there's nothing different actually? You want to switch? Intuition, reason? Mm-hmm. Mm-hmm. Yeah, that's our intuition, right? Okay, yeah, very good. Any other one who wants to supplement or provide your own thought? Okay, I'm gonna explain. Expand your intuition, and that's our first solution. That actually tests your whether you can not be confused by this, right? But later we want to use more rigorous way to show that why when you say a goat coming out from gate 3, you do have a better chance to see the car after you switch. Okay, yeah, you know the answer. The answer is that you should choose to switch the gate, right? But at the beginning, many people, when I was a college student, like 15 years ago, maybe, I was confused as well. I thought there seems nothing to change, right? You got the same chance to have a car in gate 1, also same chance to have a car in gate 2. Even I say the gate, say the goat coming out from gate 3. But actually, it's that's the kind of confusing. Right. Okay, so before we say anything, right? Before we say anything, we just are presented with 3 doors, three gates, right? Close the gates. Of course, the chance we know that the car is behind gate 1 will be 103, 103, and 103, right? The chance the car is behind every gate is 103, is equal chance, right? And then the key is that when the host opens a gate, when you see the goat, will this chance changes? A common confusion or misunderstanding is that, okay, because I still see a goat, right? I still don't know whether the car should be gate 1 or should be behind gate 2. So there's nothing change. We still believe maybe now, given you see the goat in gate 3, then we say, okay, the car can only be behind gate 1 and gate 2, right? So they should have like equal chance, right? But this is not correct. Why is this not correct? Because the choice to open gate 3 made by the host actually depends on your choice and depends on where the car really is behind. It's not like the host random pick up a gate and showing you a goat. If that's the case, for example, you random pick up a gate 1, and then the host random pick up a gate, say gate 3, you see the goat, then gate 1 and gate 2 has the equal chance because the host opening action is independent as your initial choice, right? In that case, it won't change the odds. But the problem is the host actually make his decision to open gate 3 according to your choice. Let's do a little bit of analysis on this, right? So using the probability concepts we have discussed so far, right? So we can define 3 events, right? So event 1, A1, is defined as car is behind gate 1. Event A2 as car behind gate 2. Event A3 as car behind gate 3, right? And also we have some event C as the host opens gate 3 and which reveals a goat, right? So if we want to look at the chance, right? We want to look at whether we should choose to switch to gate 2 or we stay on gate 1. We actually need to look at what's the conditional probability of A1 given C and what is conditional probability of A2 given C, right? It's exactly what we have discussed here, right? Given that the host opens gate 3, which reveals a goat, there was a chance that the car is behind gate 1, which is A1, right? Or what's the chance the car is behind gate 2, which is A2, right? We would like to compare if these two conditional probabilities are identical, right? If they're identical, then there's nothing there. We don't need to switch, right? Because you're staying on gate 1 has nothing, has an equal chance to win the car as you switch to gate 2, right? But if this conditional probabilities differ, then we can make a decision, right? Does it make sense? Right. Okay. So let us just calculate, right? So we know the conditional probability of A1 given C, according to the definition, is the conditional probability, not conditional, is the joint probability of A1 and C and over the marginal probability of C, right? That's the definition. And maybe I should write it as intersection with C, right? So the first one, I mean, here we can use the base rule again, right? So it can be written as, hello? Why this guy is dead? Hello? 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 Okay. Hello? Oh. Hello? 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 Okay. Let's see. When we leverage the base rule, this guy actually equals to the conditional probability of C given A1 times P of A1 divided by P of C, right? It's just the base rule we have introduced, right? And if we look at P conditional probability of A2 given C, it is conditional probability of C given A2 times P of A2 and divided by P of C, right? And we notice that the denominator is the same, right? So we want to compare these two probabilities. We just need to look at the numerator, right? Okay. So first, P of A1. What is P of A1? A1 is the event that the car is behind gate 1. What is the probability of A1? 1/3, right? That means like before we say anything, right? What's the probability the car is behind gate 1, right? It's 1/3. And then the question is, what is the conditional probability of C given A1? Meaning that given the car is behind gate 1, what's the probability that the host will open gate 3? Half, right? I heard that, right? Because the host know where the car is, right? Now you pick up gate 1, right? I know I can random pick up gate 2 or gate 3, right? It just random pick up 1, so it has the chance of 1/2 to pick gate 3, right? So that means the numerator for the first conditional probability is 1/6. Does it make sense? Okay. So now let us look at the second one. Right? Given the host opens gate 3, revealing a goat, what's the probability that the car is behind gate 2? Right? Again, leveraging the base rule, we want to compute first, what is P of A2? What is the marginal probability that the car is behind gate 2? It's still 1/3, right? It's the same, right? Because at the beginning, you don't see any goats or whatever, right? And you have a closed gate, you know, okay, each gate has equal chance to hide a car, right? So it still have 1/3, right? But then what is the probability of say given A2? What's that probability? Yeah, I see someone. Can you speak loudly? Why this one? Yes, exactly, right? That's the difference. You see, the host decision actually, it depends on the choice of the game player, right? So if you look at this guy, right? If this is the car, right? The car is behind gate 2. Given that the player has chosen gate 1, the host has to open gate 3, right? There's not any other choice. He won't open gate 2. If he won't, he opens gate 2, it tells you, okay, the car is behind gate 2, right? Has no choice. He can only open gate 3. So that means the probability given A2, the host open gate 3 will simply be 1. See this? Right, this is subtle thing, right? This subtle thing decides the difference. So in this case, the probability, the conditional probability of say given A2 is actually 1. It's not half. The reason is because you can only open that gate. Because you open gate 2, actually tells you everybody the secret, right? So, so now if you look at the numerator, of the second conditional probability, which is the conditional probability the car is behind gate 2, given the gate 3 is open and say goat, which is 1/3 and divided P of C, right? And if we compare with the first conditional probability, the goat is behind gate 1, given you say the host opens gate 3 and say a goat will be 1/6 over P of C, right? So now we can observe, actually, these two conditional probabilities are different, right? Does it make sense? Right? Actually, it's better to choose a switch to gate 2 because conditional on you say the host open the gate and a goat, then your winning chance by switching to gate 2 is as twice as you stay still in front of gate 1. Right? That's the subtle stuff here, right? But it's most clearly explained through our definition of conditional probability and base rule. Yeah. Yeah, that's a very good question. Okay, we can calculate right now. Yeah, so if you want to compute P of C, right? What's the probability that the host will, no matter, I mean, where car, which, at which gate the car is behind, right? The host is gonna open the gate 3 and let us see the goat, right? So to calculate this, how can we do that? Exactly, right? Just apply total probability again, right? So here we have 3 events, A1, A2, A3, right? They're non-overlapping. They're pairwise, disjoint, and they form the whole sample space, right? So we just apply the total probability, which is P of A1 times P of C given A1 plus P of A2 times P of C given A2 plus P of A3 times P of C given A3, right? And what is the probability for the third one? Yes, 0. Yeah, this guy is 0. Because given the car is behind gate 3, then you won't be able to open the gate 3 and reveal gold, right? That's an impossible event. It's empty set. So this guy is simply 0. Right? You just need to add these two guys together. And these two guys actually is just sorry, I'm gonna just speak loudly. It's just the summation of these two numerators. Right? So if you calculate, you will see that this guy will be 1/3 and this guy will be 2/3. Does it make sense? Okay, I mean, I highly recommend everyone to look into this problem. It's a very interesting problem, but it's very good practice for our understanding of probability. Okay, see you next week. Yeah.